Okay, you're going to get a second dose of economics. But it's going to be more on a hydrologic perspective. My name is David Rosenberg. I'm in the Department of Civil and Environmental Engineering, and I also have a joint appointment at the Water Lab. And a lot of my research focuses on systems analysis, trying to integrate various different components of water systems, from the hydrologic, the engineering, the management, operations, planning perspectives, and also economics and uncertainty. Today we're going to be looking at the hydroeconomic components. We're going to move even further from Wyoming to another Jordan River basin, which flows north into the Great Salt Lake, but flows south into the Dead Sea. These are some of the linkages using our project diagram that we'll be trying to address today. Mostly we'll be focusing here in the human dimensions, water management, behavior, and infrastructure, but looking at bidirectional relationships on the natural hydrology, as well as inputs from the macro geoscience, environmental, and from field scale. You'll also see a bunch of the linkages similar to what Charles was talking about in the previous talk between our human management and the policy domain. So to start with, I'll review some of the overlying hydroeconomic principles that we'll be drawing on. I'll discuss some of the informatics that went into designing the water allocation system, or WAS model, that we're using, and then focus on the application in the Jordan River Basin. We'll be looking at results for 3 situations: cooperation between Palestine and Israel over the disputed groundwater in the West Bank or the mountain aquifers, the regional effects of water conservation, and also whether there might be some other strategies to raise the falling Dead Sea level. I was hoping to present last week because it would have gone great with the Halloween theme. Okay, so let's start with some of the underlying economic principles. And I'll focus mostly on the economic aspects because I think that's probably where most of you all would be least familiar. So the late Israeli economist Gideon Fichelson noted that water is a scarce resource, which means that scarce resources have value. And he then went further on to say that desalinating seawater plus conveying it from the seacoast to the place where you actually use it puts an upper bound on the value of water in dispute. If two households or 2 irrigation districts or a city and a household or 2 countries are disputing use of some water, one of them always has the option to say, the heck with this, I'm just going to go desalinate water and convey it to use it rather than having to deal with you. Of course, whether you actually do that depends on the value of water that you're going to be putting that water to use for and how much it costs you to do that. What this tells us is that as we're thinking about managing water, we really want to focus on the value of the water, not the quantity. We have to keep track of the quantity, but the value is really the underlying issue. And we want to try and increase or maximize this value to the extent that we can. So how do we maximize value? We have to decide, since we manage water, where we're going to use it, how much we're going to use, when we're going to use it, and who gets to use it, which sectors. We have to understand what each of those sectors, and in this case, in the Middle East, we're primarily focusing on agricultural, urban, and industrial uses, but in this framework, you can easily include hydropower generation, recreation, flood protection, any other number of uses, sometimes even environmental. What benefit is actually derived from that use? And then also what the benefits are derived based on the time of use and also the location. as well as the benefits, you want to look at the cost. So how much money you have to pay to extract the water, to treat it, and convey it to the point where you're going to use it, as well as after you've used the water and created wastewater from methane gas production or municipal use or anything else, you then have to treat it, convey it, and potentially reuse it as well, and what it costs to do that. In trying to make these water allocation decisions, the economics is really embedded in the benefits and costs. We have all these limitations on what we can actually do. Some of these are physical, laws of nature, or laws of engineered or infrastructure, how much water is available, what infrastructure is in place, how we may potentially lose water through the system, and so on and so forth, as well as policies. What are our preferences or government's preferences or society's preferences for how water is used, how it should be priced, and other requirements as well. And so we'll embed these limitations as limiting or restricting what types of allocations we may allow. I'll draw a simple diagram to kind of illustrate how this works in a two-dimensional sense. And this is really straight out of a microeconomics, one of the first courses you might take in microeconomics. On the x-axis here, we have quantity, which can be of any good. In our case, we're looking at water, so the units would be some volume, acre feet, cubic meters, million cubic meters of water. And then we have on the y-axis the price, how much we would have to pay to use a particular unit of water. And a demand curve represents people's behavior, what they might do in response to different prices. If the price of a good we're looking at is particularly high, people are going to consume or use less of it. If the price goes down, they might consume more. That's one way of looking at this trade-off. This demand curve also shows the scarcity value, or how much the resource is worth. So as there's less of a particular good or available, its value goes up. As there's more, its value is less. This is why gold is a lot more valuable per ounce than silver or other metals, right? There's a lot less gold available in the world to use. The third interpretation of this curve is and that price, that value also can represent what people are willing to pay for the resource. And that willingness to pay is a representation of the benefits that they derive from using the water. So we can capture all of this in a demand curve with a few parameters. There's actually several empirical ways that you can measure demand curves. Two of the more common approaches are to observe a lot of behavior, so human behavior, how much water, say, a household is using and how much they paid for it, and try to regress or find a relationship between those parameters. Or you can build more detailed models representing household or farm-scale decisions to show how those entities might trade off their different inputs. I'm not going to go into that in a bunch more detail. The work that's underlying the WAS work in the Middle East had a lot of this detailed microeconomics underlying it. Again, the demand curve represents the benefits. We then also have to consider the costs. And what you'll notice here generally is that this is kind of a staircase step increasing function. And this is the low-hanging fruit, right? It's stuff that's really, the sources that are really cheap, that are close at hand, that are easy to develop, that have already been developed. And as you want to increase the quantity that you use, you have to go further afield, develop more expensive sources, and the costs go up. You could consider maybe this last cost step here. This represents Salt Lake City potentially tapping into the Bear River. They have to build a really big pipeline to get the water down to Salt Lake. This also represents desalination, which is now very expensive, much more expensive than most of our other options. One of the really neat things, this concept has been around for a really long time, about 2,000 years. If you read Frontinus, who managed Rome's water supply and wrote about how he organized this, one of the first things he did was he went out and figured out where all the sources to the city was. And these were all aqueducts, right? And what he noticed was the more recently built aqueducts were longer and more expensive to build. And so you generally have this increasing cost. Our net benefits, what Charles called social welfare, we'll quantify as really the area between these two curves. And in this example, you would consume up to the point where these two curves cross. If you weren't constrained, if there wasn't any other limits or policies or anything else in place, that would be your ideal quantity. So this is two dimensions, right? It could represent one particular water use sector in one city. In the Middle East example, we'll have about 45 different districts, 3 sectors, and so there's just a lot of these competing interests going on simultaneously. To the economic benefits and costs and the optimal allocation, we, of course, this was the unconstrained case, the unconstrained case, we have various constraints. And one of the main ones is conservation of mass. At any node in our model, what's coming in from either imported from other districts or shared sources or local sources has to equal what's going out, what's exported, what's actually delivered to meet demands, what may be set aside for some environmental policies, or what may be leaked. This is another way of thinking of this. This is just a spatial representation or a pictorial representation of the continuity equation that Christopher showed in the first lecture. We have this for fresh water and similarly for recycled water. And we can also have continuity equations to say how fresh water that's used to meet demands becomes wastewater, is treated, and then can be recycled and then made available as well. This would all be connectivity and constraints at the districts. We then also have a regional sets of connectivity, and here the arrows could represent either physical infrastructure or engineered infrastructure or natural conveyance, river courses or wadis. And the black arrows represent fresh water, and the red arrows represent recycled water. What's interesting to note about this arrow here, it's a schematic that actually represents water that comes from Tel Aviv's wastewater treatment plant, is recharged into the groundwater, flows through the ground, and then is pumped out by Israeli farmers in the Negev. We have about 45 districts, and as you're trying to mathematically represent regional connectivity, this would give you a matrix with where, say, the rows would be where you start and the columns would be where you end. It would have about 2,000 elements in it. But we actually only have 110 links. So most of that matrix is very sparse. It's all zeros. And we can make use of some of the computational advantages that David Stevens talked about for work on these sparse matrices. The slide here is a little bit notation heavy, but the key thing to keep in mind here is we try and include infrastructure management and policies, and the model's trying to determine how much local sources should we use, how much should we import, how much should we treat, how much should we use, how much should we set aside. Each of these we can also specify with a minimum or maximum bound. So we can prescribe the policy or limit that forces that decision, and we can set these values to whatever we choose. All told, as you combine all those things together, you end up with about, for the Middle East example, which is 3 countries and 45 districts and 3 different sectors, you end up with about 13,500 equations and 48,000 decision variables, which means you need a good modeling system, a good support system to actually organize all that data together so that you can keep track of it and really understand at the end what it all means. This shows a little bit of how the decision support system is organized. As far as the modeling perspective, we need as inputs trying to define the regional layout of countries and districts and water use sectors and nodes to include in the model. We have to define the demands, the supplies, which of those supplies are shared amongst different countries and how much they own of each of those supplies, what other infrastructure is in place, be it conveyance, treatment, wastewater treatment, desalination, and so forth, what are our environmental requirements, and what are our policies. I spent a significant amount of time actually organizing the DSS around this so that the user could control all of this at runtime. You didn't have to rewrite every line of the code in the model and in the interface and in the database and in the optimization engine and in the display to actually test different layouts or schematics. And getting that integration together is, I think, a really, really, really important, important aspect. As you think of most water management models, and here where I would include all the HEC products, SWAP, which is a statewide agricultural production model for California, SWAT, and other programs, they tend to lump all this stuff together in a single decision support system, and you can't actually extract or take out individual components of it. That becomes really, really key as you want to look at or doing research with management models. On the output side, our system model tells us the net benefits from water use for the region. We get both for individual districts and by individual sectors, as well as the aggregate sum, how much each sector and each district paid for their water, what quantity they used, and what the shadow value is associated with particular constraints. Shadow values are a really nice feature of optimization modeling. And basically what they say is that if you have a constraint and it's binding, if you were to relax that constraint a little bit, it would tell you how much your objective, your net benefits would increase. So it's a way of doing sensitivity analysis very quickly without having to rerun the model. And so here we can look at the shadow values for if we expanded a pipeline or a canal by a little bit, how much additional benefits we would get. Or if we had an additional supply, how much would that help us? And also, what potentially would be the benefits of cooperating. So I talked a little bit about the decision support system and how for most common water management software, these are just all bundled together in this thing we would call the model. But really, the model is just a computational engine. And there's a database and a user interface and graphical display that are managing or interacting with the model. And if you think about decoupling those, you can then potentially substitute in other models. And you can avoid or get around the issue of trying to have to move or manage your data from one platform to another. Or you can use a centralized platform to manage all your data and serve it to the various different uses. Okay, let's turn to the Jordan River Basin in an application and see some model results. This is a picture of the northern end of the Dead Sea from Jordan looking west. You can see that the area is extremely arid. As far as precipitation, most of it falls in the north, in Israel and the occupied Golan Heights. And moving south, we decrease to less than 2 inches, 2 inches per year. The graph here shows the time series of, or the annual rainfall for Jerusalem over the last, over a long while. It's hard to read the numbers in there, but you can also see there's a lot of variability from year to year too. And that plays a very important aspect in water management. In terms of surface water, there's about 1,300 million cubic meters per year on average available in the Jordan River Basin, which is the northern part shown in brown here, this outline here. And for those of you who are used to thinking in acre feet, 1.3 million cubic meters is about, or 1.3 billion cubic meters is about 1 million acre feet. So this is not a very large amount of water. The basin area, the Jordan River Basin, is about 1,800 square kilometers, which is about the size of the Bear River Basin. The figures show different views of different tributaries and rivers in the basin. These are all taken on the east side in Jordan, and I think generally emphasize that most of the precipitation in the basin runs off and accumulates in this upper portion here. In terms of groundwater, it's split between a bunch of different aquifers. The solid line here shows the mountain aquifers, which are contested currently between the Palestinians and Israelis. There's the coastal aquifer and the Gaza aquifer, as well as aquifers on the East Bank in Jordan. All told, these are another about 1 billion cubic meters. And these numbers represent what hydrogeologists have determined is the safe yield of these aquifers, which is different than what's actually being extracted from them. In terms of demographics, about 15 million people live in the basin, or water that's delivered, exported out of the basin and used. The highest growth is in Jordan and in Palestine. So the demographic issue is going to get even worse in years to come. In terms of infrastructure, the Sea of Galilee, which is also what the Israelis would call Lake Kinneret, or Palestinians would call, or Arabs would call Tiberias, is in the north and provides significant holding capacity for most of that significant or large precipitation that falls and runs off in the north. Israel in the 1960s built a huge conveyor to extract water from the Galilee and export it out of the basin and all the way south into the Negev desert. Jordan did a similar thing on the east side, and they also pump their water 1,000 meters up to Amman. There's a Unity Dam, which Jordan recently built, and the question marks and exclamation points there are that the dam's been in operation for about 3 years now, but has never seen more than about 15 million cubic meters of storage in it. And most of that's due to the fact that the Syrians have already developed all the runoff that would accumulate into the dam. Two of the major projects that are under consideration, and I'll look at the second one in a second, are the DZ conveyor, which would tap fossil groundwater in the south to convey it to Amman, and the Red Sea, Dead Sea Canal, which would take water out of Aqaba at the north end of the Red Sea in the south and convey it all the way north to the Dead Sea. We'll look at this example in a second. You can summarize the current issues in the basins, and then we'll get to the results, which look at this as contested water rights in the mountain aquifers. What's the potential role for water conservation in a region that's faces extreme water scarcity already, and whether water resources can support future population growth and environmental needs. There's also issues about sharing, cooperating, or building private desalination plants, and how water links to other disputed issues between the Israelis and Palestinians. So the first hydroeconomic model results I want to look at are related to cooperation between Israel and Palestinians over use of the mountain aquifers. And this is taken from Frank Fisher and Annette Huber-Lee and a team of Israeli, Palestinian, and and Jordanian researchers who worked for about 10 years on this from 1990s, mid-1990s to 2003 or so, and was like the first efforts at this work. So the graph here shows the percent ownership of the mountain aquifer. So on what would be your left is Israel owning 80% and Palestinians owning 20%, and the converse, Israel only 20% and Palestinians owning 80% of the aquifer. We'll first look at with the bars, which show the value to each individual country if they were to acquire a 20% larger share of the aquifer. And so what you can see here is that for Palestine, when they move from 20 to 40% ownership, that's worth about $50 million. As they acquire another 20% share, that new share is only worth about $10 million. And finally, as they have most of the aquifer, the additional water that they gain is not worth very much. It's only a few $1 million. And you see the converse for the Israelis as their ownership moves from very low to higher, the value decreases. And this represents the downward sloping demand curve and the area that would be under it. There's just less value there. These model results were for a scenario where all the Israeli and Palestinian districts were separated, meaning you couldn't convey water from a Palestinian district to an Israeli district or vice versa. When you introduce those connections between the countries, and keep in mind the West Bank is about 50 kilometers north to south, so this is a very small area. It's actually really easy to physically connect it, and the West Bank is much higher than the surrounding Israeli area, so it's easy to send the water by gravity flow down towards Israel, either on the surface or allowing it to flow through the groundwater aquifers. We can see the value of cooperation. And this value is the overall net benefits with cooperation in place minus the overall net benefits without the cooperation. And the really key, striking take-home message from this slide is that in all cases, the value of cooperation, regardless of who owns the aquifer or how much, it's larger than the individual value of the ownership to the individual country. Here it looks like this bar is larger. You would actually want to think about moving it over here, and in which case the value of cooperation would be higher. And this is true regardless of how you actually partition the ownership or assign the ownership of the aquifer sources. A very, very key and interesting finding. And what this tends to say is that, for example, when in this situation, when Israel owns most of the aquifer, they can't really do the best things, the most economically efficient or viable activities with it. The Palestinians can do a lot more economically efficient or viable activities with it, so it's worth it for the Israelis to trade with the Palestinians. And the trade works like this. The Palestinians give the Israelis money, and the Israelis give the Palestinians water. That's in the theoretical sense. Right now, with the Israeli occupation of Palestine and the West Bank, the current ownership regime sits right here. So there's issues of whether by trading you might want to encourage having to pay or encourage, what do I want to say? There could be the complication of by assigning this particular ownership percentage, then the Israelis would benefit additionally because they've taken this volume of water, but you can actually separate these things and negotiate over the ownership of the resource regardless or different from whether you should actually trade or cooperate over using it. Cooperation and ownership are different. Let's turn to a second example, which is just for Jordan, and work I did through 2006 and 2007. where we looked at what would happen if you implemented a countrywide regional program of targeted water conservation programs. And these water conservation programs would be targeted only to urban users who were going to save the most water and money by retrofitting their leaky toilets and their faucets and their shower heads with water-efficient appliances. The results, the numbers on the map show the shadow value of water availability. So again, this shows the additional benefits that would accrue if one more unit of water was available in each of these locations. Blue shows the scenario where water conservation is in place, and red shows the scenario where no water conservation was in place. And again, or here what you'll see is a dramatic reduction in the scarcity value of water as you implement conservation measures. Keep in mind, a high scarcity value is not very desirable. It means there's lots of shortages. People are using very little water and they're not very happy about it. So having reducing that scarcity value is a very desirable thing. What's interesting here and not shown on the results is that the actual water use doesn't change at all in these scenarios. Oman is still using the same volume of water. There's just getting a lot more economic benefit out of that water that is used. We can quantify those all benefits if you add up the total benefits over the for the 13 governments in the country. It's on the order of $3.5 billion. And you can see that the conservation improvements are much larger than if you add more infrastructure, so expanding conveyance or water supply sources, or even introducing leak reduction in their distribution system. Amman and most of Jordan has an unaccounted water of about 40%, which means that for every 100 units that they supply and put into their distribution system, only 60 shows up on customers' water meters. About 20% of that is physical leakage, so it's actually lost out through the distribution system, and the other 20% is stolen. So fixing those issues can have huge economic implications as well, although not nearly as dramatic as targeted water conservation programs. Okay, the third and final application, which is looking at how we might potentially raise the Dead Sea. Water is very scarce in the Middle East, and nearly all the water going into the Jordan River is now extracted. The lower Jordan River only sees about 100 million cubic meters per year of the historical 1,300 or 1.3 billion that historically flowed. This has caused innumerable problems ranging from a 30-meter drop in the Dead Sea level since 1960. This drop has accelerated to about 1.2 meters per year. 1.2 meters per year in the last few years, 33% declines in surface areas, and assorted other environmental problems. One of the solutions that Jordan, Israel, and the Palestinians have proposed is building a conduit from the Red Sea north to the Dead Sea. And this would basically involve an intake at Aqaba, a canal or piped facility along the 180-kilometer length. They would generate hydropower because you would be moving water from sea level to minus 400 meters, so there's a net head there. Desalinating some of the water and then pumping the fresh water to Amman and dumping the brine waste into the Dead Sea. This project has always struck me as ludicrous. It was ludicrous when I looked at it for just in Jordan modeling scenarios, and that was when its costs were only $2 billion in capital costs. They've now revised them to $5 billion. The World Bank has been assessing the feasibility, and it struck me as, wow, we could look at our hydroeconomic framework to see if this might make sense. And I'll wrap up with just a quick summary of what some of these results looked like. So on the bottom, we show the flow to the Dead Sea. And this is a constraint in the model. We're forcing the countries to deliver the water. This is the environmental policy we want to impact. And on the y-axis shows the change in expected costs and how much expected costs, so how much benefits will decrease if we impose this type of environmental management on the system. And each of the traces then shows a variety of scenarios, physical, infrastructure, conservation, and others that we might go about achieving this. Two things to look at here. That in all cases, as you try and restore the Dead Sea, costs go up, which means these countries are not going to have very many incentives to actually go along with this restoration program, even if you build the new infrastructure to do this. One thing to note, though, is that conservation and new local infrastructure programs and a much smaller Red Dead project that only desalinates, that only generates hydropower are two of the more favorable of all the alternatives considered. The option here is in orange is what the three countries are proposing. This means that beyond infrastructure, the organizations such as the World Bank or environmentalists really have to think through another program or another set of incentives that are going to encourage countries to deliver water to the Dead Sea. Building them new infrastructure alone isn't going to solve the problem. I'll skip through this slide with time and then wrap up with some of the conclusions, which are first that systems modeling can integrate numerous aspects of a water system of interest, including our hydrologic, engineered, management, and policy components. As we think about hydroeconomics, we want to allocate water by value, not necessarily by quantity. This can allow us to separate the ownership from the use of the resource. And when we do this, we can see that the value of water disputed by Palestinians and Israelis is very small. Remember, the results were about $50 million of what the value was for the Palestinians getting another 20% of the mountain aquifer. And for the Israelis, it was even smaller. That amount in regional context is trivial compared to the cost of Israel occupying the West Bank, buying new fighter jets or other realms. It's really very small. Water conservation can generate substantial national and regional benefits. And finally, the infrastructure alone will not raise the dead. There are several references if you want further information. And with that, I'm happy to entertain questions, and I think